differential calculus thoroughly. Yes, you are happy with differential calculus. Any function given, you know how to differentiate it. You have experienced that provided a function is differentiable, you can successfully differentiate it. Maybe procedure may be lengthy, maybe little time consuming, but you will be successfully able to differentiate any given differentiable function. You must have noticed it. Second thing, given any differentiable function, when you differentiate it, you get a single function as derivative. There will be no confusion. By applying different procedures, you won't get different functions as derivatives. Same function, maybe in different forms, will be obtained as derivative. Yes. Now, our objective will be sort of a reversal of the process. That given a function, we were finding the derivative. Now, we will be given derivative, we will have to find its primitive. We will be given a function, we have to find a function which when differentiated gives this. That will be our objective. The process will not be as straightforward as differentiation. We come across several obstacles along our route. We come across some difficulties also. We will learn how to manage all these things. Okay. Let us have a formal beginning. Suppose f of x is a function defined over an interval I. Some interval, f is a function. Then a function g is called an antiderivative for f over I if two things I require. F is any function defined over I. A function g is called an antiderivative if g is continuous over I and derivative of g is f in the interior of I. If I is a closed interval, I do not require derivative of g to be f at the end points. I need it to be the derivative only in the interior, but continuity I want everywhere. If the interval is closed, even at the end point I will not have two-sided continuity, at least one-sided continuity relevant, one-sided continuity I must have. Agreeable? Then g will be called an antiderivative for f over the interval I. Okay. So, for this function, this is the derivative. For this function, this is an antiderivative. Is an antiderivative because when I differentiate this, I get this. Agree? Is an antiderivative because when I differentiate this, I get this. Okay. This also, this also is an antiderivative for this. Even when I differentiate this, I get this. also is an antiderivative, also is an antiderivative. So what is it? One point that we observe is, whenever an antiderivative exists, there will be infinitely many antiderivatives. Unlike derivative of a function, antiderivative is not unique. There will be infinitely many antiderivatives if there exists an antiderivative. Agreeable? One more thing. Suppose a function has two antiderivatives. Can you connect those two antiderivatives? Should the difference between the two antiderivatives be a constant? In this case, I found this is one antiderivative, this is another antiderivative. What is the difference? Is a constant. Should this happen between any two antiderivatives of any function? Suppose f is a function, g is one antiderivative, h also is an antiderivative. Means what? G is continuous over that interval, h also is continuous over that interval, g prime is f, h prime is also f. My question, should g minus h be a constant or can it be something else also? Should be a constant. Any justification? If g prime and h prime are equal, why should g minus h be a constant? Why can't it be something else? This is what I am asking for. G prime and h prime are equal. I consider the difference. I need to know whether this should be a constant or can be something different also. You are saying it must be a constant. I need a justification. Okay, for a constant I know the derivative is 0. Does it mean that only constant function gives 0 as derivative? There may be some unknown function having derivative 0 which you might not have studied, which your teacher might not have told. You have a doubt. So it needs a justification. You can justify. With your knowledge of first PU differential calculus, you can justify. How? Very simple. So your objective is just to show that if there is a function f with the derivative equal to 0, you need show that this must be a constant. This is your objective, reduced objective. Agreed? Okay. Assume against the required, assume the contrary, assume that f is not a constant, assume that f is not taking the same value throughout, f is taking different values at least at 2 points. Suppose f of a is different from f of b. I need to show that they are equal. At any pair of given points a and b, f of a and f of b are equal. This is what I want to show, to claim that f is a constant. Assume f of a is not equal to f of b. Okay. Without loss of generality, I assume a less than b. Consider the interval a b. Is your function continuous over the interval? Yes. You are told derivative is 0. It is differentiable, must be continuous. Is your function differentiable also in the interval? Yes. Are you reminded of a mean value theorem? Whenever a function is continuous and differentiable over an interval, what happens? There exists a point in the interior of the interval such that at that point the derivative is very good, very good. Did you arrive at a contradiction? Yes. You have assumed f of a and f of b are not equal. So you are getting f prime c not equal to 0. Are you not contradicting that? Are you not contradicting this? Okay? You are convinced that if a function has derivative 0, it must be a constant. Okay. As a consequence, I notice if a function has infinitely many derivatives, not if, every function having a antiderivative has infinitely many antiderivatives, difference between any two antiderivatives must be a constant. Agree? If g is an antiderivative, then all other antiderivatives are obtainable from g of x plus c, where c is an arbitrary constant. Agree? So, for e to the power x, the set of all antiderivatives is this, where c represents a constant. For cos x, the set of all antiderivatives is this, where c represents an arbitrary constant. Agreeable? Okay. Consider a function having an antiderivative. Immediately when I write this statement, you may raise a question: does there exist functions not possessing antiderivatives? I will try to answer it a little later. For the moment, let this be a function having an antiderivative. It will have infinitely many antiderivatives. I consider their collection. The collection of all antiderivatives, the set of all antiderivatives will be called an integral for f and will be denoted by let me denote the symbol also, symbol representing the independent variable. Let f of x be a function having an antiderivative. Then the set of all antiderivatives of f is called the integral of f with respect to x and is denoted by So, if a function has an antiderivative, it will have infinitely many antiderivatives. The collection of antiderivatives is called the integral of f, the integral of f, an antiderivative, the integral. Antiderivatives are more in number. This is unique, the integral, or primitive also I may call it, and is denoted by this symbol. This is just an elongated S. The symbol was first used by Leibniz. The use was made in 1675. From 1675 onwards, this symbol is being in use to represent integral of a function. Leibniz was the first person to use it. Why did he use this letter S? First letter of the word summation. What summation has got to do with the integration? We will learn it later, not for the present. Okay. So, agree? Agree? In general, agree? This is the definition. Okay. But in our study of integral calculus, we will have to write integral of a function several times. When a procedure is to be repeated number of times, we feel the representation that we make use of for that item also must be enough simple. So we do not write every time these flower brackets and this thing every time. We will have an understanding. Instead of writing like this, we simply write e to the power dx equal to e to the power x plus c. C is an arbitrary constant with this in the background. When we write this, actually it means this, but we are not mentioning every minute detail of that expression. Okay? So throughout our study, this will be the notation we will be making use of. For a arbitrary function, I will simply write g of x plus c. Okay. Next point. A function, if it has antiderivative, it will have infinitely many antiderivatives. Collection is called integral, and we know how it is represented. Okay. Now next is we made the statement, if a function has an antiderivative, immediately the doubt arises, will a function have an antiderivative always? If it does not have an antiderivative always, under what conditions it will have an antiderivative? When it will not have an antiderivative? I will try to answer the question only partially. It has been established that every continuous function has an antiderivative. If a function is continuous, certainly it will have an antiderivative. Does not mean if a function is not continuous, it won't have an antiderivative. It may have, may not have. But if a function is continuous, definite, it will have an antiderivative. You said certain functions will not have antiderivatives. One example, yes, I can provide. Suppose you consider this function. Everywhere it is continuous. At every rational point, I am defining the value to be 0. Irrational point 1, 0 and 1 values are immaterial. You can choose any two numbers different from each other. Any function like this or this particular function does not possess an antiderivative. Okay. Continuous functions have antiderivatives. Does not mean discontinuous functions won't have antiderivatives. Can I provide an example of a discontinuous function having an antiderivative? I can. Very simple. Consider this function. Is the function continuous everywhere? Yes. How did I check? Simple. Simply find the limit of this as x tends to 0. Won't you get the limit as 0? Yes. How? Sandwich theorem. Limit mod of x square sin 1 by x lies between 0 and x square. Mod of x square. Mod of x square same as x square. Limit of 0 is 0. Limit of x square is 0. Limit of the mid function also must be equal to 0, continuous. Is the function differentiable also at 0? Yes, use the definition of derivative at 0. Derivative at 0 defined to be limit h tending to 0 of f of h minus f of 0 by h. F of 0 is 0, f of h is h square sin 1 by h. Is not the limit existent and equal to 0? Yes. Again, use of sandwich theorem alone. Okay. Function is continuous, differentiable. What is its derivative? Am I right on differentiating this? Yes, 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 yes. Any correction needed? Is it okay? Yes. What is derivative at 0? We have just now obtained 0. Yes, yes. For this differentiable function, this is the derivative, or in other words, this is derivative for this. Therefore, this is antiderivative for this. This is a function which is discontinuous at 0. Discontinuous at 0 for the reason it is not defined at 0. Sorry, it is defined at 0. Limit of it as extends to 0 is undefined, does not exist. For that reason, this function is discontinuous at 0. Still, it has an antiderivative. This is one such antiderivative. Okay. One more example. As before, the function is defined everywhere, continuous everywhere, differentiable everywhere. Find the derivative. Easy to find using definition of derivative at 0 and derivative at a point not equal to 0. Am I right? Just check it once. It's okay, I think. Yes. Again, we notice this function may be defined everywhere, but is not continuous everywhere, is discontinuous at 0. Discontinuous at 0 for the reason limit as extends to 0 does not exist. Here is one discontinuous function having an antiderivative. Here is another discontinuous function having an antiderivative. What is the purpose of providing two examples of same kind? There is a difference between these two functions. This is discontinuous but bounded. This is discontinuous and unbounded. So, in both varieties we can have functions having antiderivatives. Exact set of conditions to be satisfied in order that a function may have an antiderivative. I don't have, I can't give. Some people say it's still an open question. I don't know, I do not have latest information, but I am definite that if a function is continuous, it will have antiderivative. In other cases, may have, may not have. Next problem. Suppose a function is continuous. Theory says it has an antiderivative. Continuous has an antiderivative. We know what the antiderivative is. Also is continuous. According to theory, has an antiderivative. But the techniques we are going to learn here will not be sufficient to obtain an antiderivative for this. This looks like a very simple function, is a simple innocent continuous function. having an antiderivative, but determining antiderivative will not be possible for us. As far as our study is concerned, this will be practically not integrable, theoretically integrable, practically not integrable, because the integral involves many non-elementary functions. By elementary functions I mean polynomials, rationals, exponential functions, trigonometric functions, inverse trigonometric functions, logarithmic functions. This involves other functions which are non-elementary. Therefore, our methods will not be sufficient to obtain an antiderivative for this. Like this, there are many more functions which are known to have antiderivatives, but practically we will not be in a position to obtain that antiderivative. Our methods fail to integrate those functions. As far as our study is considered, they are non-integrable for us. Theoretically integrable, practically not. Few more functions. Not involve integral does not involve elementary functions. Many more are there. None of these functions we will be able to integrate, even though theoretically they are known to have antiderivatives. Okay. So our study now gets reduced to a very simple job. We will be given a function. We will be told that the function will have an antiderivative. We will be told that the function is practically integrable, and we are asked to integrate the function, obtain an antiderivative. We will be knowing that the function possesses an antiderivative, it is practically obtainable also, and we have to perform integration, get the integral or get the antiderivatives. Okay. To obtain integrals or antiderivatives, we will have number of techniques. Mainly the techniques we are going to study are only 4 techniques. But the difference is the techniques are not as elegant as our differentiation methods. For differentiating a function, we have a very perfect algorithm. Following a certain procedure, we can differentiate any given function, however complicated it may be. Here, the procedure is not that simple. The method that you have to apply will depend on form of the function. For example, for this function, a standard result alone will be enough. I will be able to carry out the integration. Suppose I have a function like this. It is not practically integrable. Now I will require method of substitution. Now integration by parts. Decomposition method. Use of a reduction formula. Changes from form to form. We cannot predict, without studying the form of the function, we cannot predict which is the most efficient method to carry out that particular integration. So some difficulty will be involved. It will not be as direct as differentiation. We will require some more preparedness for carrying out integrations. Before taking up any of these techniques, the most required thing for an efficient handling of any of these techniques is a collection of some results, basic results, which we call them as standard results. Without these standard results, any of these methods cannot be applicable, cannot be made use of. So we will first prepare a list of standard results, then proceed to study these methods one by one. N may be any number, any rational number. Why should n be an irrational number? Why should n be a rational number? We do not know the meaning of x to the power n when n is irrational. What is x to the power root 2? Do you know the meaning? Okay. Which function, when differentiated, gives x to the power n? Very easy to guess. For x power n, derivative is nx power n minus 1. Integral will be x to the power n plus 1 by n plus 1 plus an arbitrary constant will be the actual integral. Without c, it is only an antiderivative. With c, it will be an integral. Not an integral, the integral. Does this apply for any value of n? No. Because we find n plus 1 in the denominator. N cannot be minus 1. If n is minus 1, what will you do? When the numerator of the fraction to be integrated is 1, you may simply write dx as numerator here. No fault in writing this as dx by x. We may write it. No need to write it as 1 by x dx. We may write it as dx by x also. Okay. Which function, when differentiated, gives 1 by x? Very simple. Again, does this apply for any value of a? No. We have log a in denominator. Must be meaningful. At this moment you cannot guess. By guess you cannot determine the function which when differentiated gives log x. I will provide you the function. You can verify by differentiating that and checking whether you get this as the derivative or not. Actually this has been obtained by applying a special method, the method of integration by parts. I am including it now itself so that my list may be complete. I need not go on including results at different stages. Let the complete list be available with you at the beginning itself. With that objective, I have included it here itself. Just check when you differentiate this. Do you get this? Yes. Are the candidates provided with the list, complete list? So no need to copy the list on the board again. Any result, if you have any doubt, you can cross check by differentiating the function on the right side and finding whether you get this function to be integrated as the derivative or not. Can be done very easily. Okay? Complete list has been given. So there will be no need to again rewrite it on the board. No derivations will be provided to you at this moment. You can only cross check by performing differentiation. Remember, this differentiation method is also one efficient method in the examination. Suppose you have a question on indefinite integral. You are provided with 4 options. In the examinations you are going to face, you are always provided with options. Suppose the 4 options do not differ from each other in major part. There are only coefficient differences. Minor differences are there in the 4 options. By just differentiating one of the options, you will be able to determine which exactly is the right answer. One efficient method which can be followed even in the examinations. Okay. You have a complete list of standard results. Now we can proceed to apply the methods of integration. We will follow the list one by one. First method, or before applying the first method, I have one more method which may be numbered as method 0, use of one theorem. Suppose you know for the function f of x, g of x is an antiderivative. Then you can be certain for the function f of ax plus b. How this f of ax plus b obtained? From this replacing x by a linear function. Don't forget, replacement is to be made only by a linear function. Then integral will be this. An indefinite integral will be this. An antiderivative will be this. Easy to verify. Differentiate this. What do you get? 1 by a into. What is derivative of g of ax plus b? It is g prime ax plus b into derivative of ax plus b. Derivative of ax plus b is a. What is g prime ax plus b? Is f prime ax plus b. Agreeable? Okay. By this alone, I can integrate so many functions. You know, for x to the power n, derivative is x to the power n plus 1 by n plus 1. For x to the power 2015, not derivative, I am sorry, integral is x to the power 2016 divided by 2016. For 2x minus 3, got from x to the power 2015, replacing x by a linear function. The theorem applies. Replacement is done by a linear function. Theorem applies. Integral will be 2x minus 3 to the power 2016 divided by 2016, got by applying the formula. One extra thing you have to write in the denominator a, the coefficient of x. If you want, you can cross check differentiating this, verifying this. For the function log x, I know integral is x log x minus x. This is function obtained from log x, replacing x by a linear function. Theorem applies. My integral will be one by 3. I'll write later. At the end, I'll write it. First, let me complete that standard form. X log x minus x. Agreeable? Which term I dropped? Minus? Not the number of the term. What is the content of that term? It has been swallowed by that C at the end. Agreed, I think. You know integral of cos hyperbolic x is sin hyperbolic x. So integral will be agreeable? Yes. The function I am asked to integrate is simply cos hyperbolic 10x. Therefore, integral is agreeable. Is not the denominator simply 2x minus 1 whole square? I don't know. Yes. For x power minus 2, I know integral is x power minus 1 by minus 1. So for this, the integral will be minus 1 2x minus 1 to the power minus 1 divided by minus 1 again divided by the coefficient of x in the expression 2. Agreeable? Is it not wrong? It should have been 2. Apply the method of completing squares. Do we find the integrand in a standard form? Yes. We find it in the form 1 by x square plus a square with the x replaced by 2x minus 1. For 1 by x square plus a square, I know the integral is 1 by a tan inverse x by a. So for this function, the integral will be 1 by a tan inverse x by a, x is 2x minus 1 by a root 2, whole thing without forgetting again divided by, to be divided by a is 2. Let me have different coefficients. Okay, let me have some other number. Otherwise, you may argue in a different line. We will take 4 outside, then we will be left with x square minus x in denominator. We can factorize it, we can apply partial fractions, go to decomposition method. Now, decomposition is not applicable, I think. Okay, let us try this theorem method. We find the function to be integrated now in the form 1 by x square minus a square. For 1 by x square minus a square, it is known integral is 1 by 2a log x minus a by x plus a. So for this, the integral will be 1 by 2a log mod of x minus a by x plus a. X is this by x plus a, whole thing without forgetting must be divided by the coefficient of coefficient of x agreed. Yes, 2x minus 1 whole square plus 2. Expression now is in the form 1 by root of x square plus a square. For 1 by root x square plus a square, it is known that an integral is an antiderivative is sin h inverse, sin hyperbolic inverse x by a. Do we have coefficient 1 by a outside? In that formula, do we have coefficient 1 by a outside? No. We get 1 by a when there is no radical sign here, and we get 1 by a whenever there is we get 1 by a whenever there is no radical sign. When there is radical sign, there will be no 1 by a in the right hand side. So formula applying sin hyperbolic inverse. X coefficient, not 1 by a, it is a, the coefficient of x, the coefficient of x in this expression, not 1 by a sin h inverse x by a I am writing, integral is sin h inverse x by a alone, but outside 1 by a I must write, because I am applying the theorem. It is not a outcome of an a standard result, not a direct application of standard result, it is extension of standard result. So this 1 by a. Agreed, I think. Again, same old procedure. We will apply the method of completing squares. If you want, for convenience sake, I will have this coefficient as 4. So that applying the method becomes slightly simpler. Even otherwise I can do it. I can write it as root 2x minus something whole square. To avoid that, let me have an integral perfect square coefficient, so that I can write. In order to get 4x square, I must square this. To get the double product as minus 3x, I must write minus how much? 2x into this number must become 3x. 2 into 2x, 4x into this number must become this 3 by 4. As a result of squaring this, I get 9 by 16, but my requirement is 1. How much more I must add? 7 by 16. The integrand is in the form root of x square plus a square, with the x replaced by a linear function. Applying the theorem, I get the integral. Let me first write 1 by a outside. This is that coefficient. Okay, then formula application. X by 2 into the same expression there is a sign plus or minus plus a square by 2, a square is 7 by 16 divided by 2 into sin hyperbolic inverse x by a. X is 2x minus 3 by 4 divided by a, root of this, root 7 by 4, agreed, over, plus a constant of integrations. Slight simplification is possible. I am sure you will be able to do it. Integrand is in the form e to the power ax sin bx, another standard function which is in our list. E to the power ax by (11x). Should the whole thing be divided by another number? No, as it is we applied the formula. No replacements have taken place. This is e to the power ax, a equal to 5 into sin bx, b equal to 5. As it is, the formula has been applied. No extra replacements have been made. Direct application of the formula, the answer is obtained. Okay. These are some of the two simple integrands which are integrated without the application of any one of the techniques of integration, just the standard results. One additional theorem was sufficient, we could get our answers. Now slightly more complicated functions will require the help of one of the techniques of integration. The first technique that we have to learn is the decomposition method. The theorem I am going to apply will be simply states integration is a linear process. For any linear combination of two functions f1, f2, integral also will be linear combination. Linear combination of integrals of f1 and f2. So it will be very simple. If a function can be obtained in a linear combination form, if a function can be obtained in the form k1 f1 plus k2 f2, no need that we must have only two functions, we have more functions also. We can apply an extension of the theorem, get the integration performed easily. For example, as it is, the function to be integrated is not a standard function. You cannot obtain it from a standard function replacing x by another linear function. The theorem we cannot make use of. If integral f of x is g of x, integral f of ax plus b is 1 by a into g of ax plus b, that theorem I can't make use of. So I have to go for another some other method, some technique I need. The technique that helps me now is decomposition. Even though this function as it is not easily integrable, I can break it into a sum and find it as a sum of two easily integrable functions, get each function integrated separately, combining can get the integral of the given function. What do I do? Simply break this into partial fractions. Is the fraction considered a proper fraction? Yes. So can it be directly split into a sum of partial fractions? Yes. How many partial fractions you are going to get? 2. First will have denominator x minus 1, the second one will have denominator x plus 3. Both the partial fractions will have some numbers, constants as numerators. Agree. What will be this constant? What you do is simply apply the value at which this vanishes. At which point does this vanish? x equal to 1. Apply that value everywhere except in this factor. What do you get? Is this numerator. This will be apply x equal to minus 3 everywhere except in this factor. Minus simply 9 by 4 plus 9 by 4. I didn't check. All of you are predicting that numerator is 9 by 4. I accept that. Okay. Minus 1 by 4 is a constant. I can keep it outside the integration process. The function to be integrated here is just 1 by x minus 1 according to one of my standard results. Integral 1 by x is log x, 1 by x minus 1 which is similar to 1 by x with x replaced by linear function will be log x minus 1. To make the function meaningful at more points, we provide that modulus. Otherwise, it will be undefined at x equal to 2. It will be undefined at x equal to, sorry, not x equal to 2, x equal to minus 1, minus 2, x equals 0. At those points, it will be undefined. Now, it is defined at more points. It is undefined at only one point, x equal to 1. At x equal to 1, we need not bother. Even this function is undefined at x equal to 1. We need not have the integral defined at x equal to 1. When the integrand itself is undefined at x equal to 1, why should the integral be defined at x equal to 1? Okay. Plus. If you want, you can combine the two terms using properties of logarithms. If necessary, can be done. If you want if you are provided the options in that form, you have to combine them. Otherwise, no need. Again, the function to be integrated is a rational algebraic fraction. Whenever your function to be integrated is a rational algebraic fraction, the only method you have to depend upon will be the decomposition method. You will have to try to decompose the fraction into a sum of several simpler fractions, then carry out integration. But direct decomposition not possible, because my function is not a proper rational function, it is an improper rational function. You have the degree of numerator same as the degree of the denominator. Whenever numerator degree is equal to or more than degree of denominator, we call it an improper fraction. Improper fraction cannot be directly split into partial fractions. First you will have to obtain it as a polynomial which is obtained as quotient plus a proper fraction. Everything I will perform simultaneously. This obtained by inspection. You divide this by x square plus 2x, you can have only one term in the quotient and that term must be 2 only. Okay. Then to obtain this numerator, I applied x equal to 0 everywhere except in the factor x. X is removed from this, x plus 2 remains, numerator no change, apply x equal to 0, you got this. To get this, apply x equal to minus 2 everywhere except in the factor x plus 2. X plus 2 is removed, x remains, replace x by minus 2. In numerator everywhere replace x by minus 2, you get the numerator of the second partial fraction. How much? 15 by 2. For this, the integral is 2x. Again, one more case of a rational algebraic function. When the function to be integrated is rational algebraic, I have already told you, only method you have to depend upon is the method of partial fractions. In general, according to the theory of breaking into partial fractions, you have to assume two partial fractions. First we will have denominator x square minus 1, second x square plus 4. Numerator of the first, because denominator is quadratic, will be of the form ax plus b. Numerator of the second will be of the form cx plus d. Or if you want, you can break this into a product, x minus 1 into x plus 1 into x square plus 4. Then you will get three partial fractions. First one, having denominator x minus 1, will have a constant in numerator. Second one, denominator x plus 1, numerator constant. Third one, denominator x square plus 4, numerator ax plus b. We will have to find the constants involved, but no need to go through all those complications. Your expression involves only even powers of x. Therefore, no need to break this even. If I break this, I will not find my expression as an expression involving only even powers. I will retain this like this only, break it as it is into two partial fractions, one with denominator x square minus 4, x square minus 1, second with x square plus 4. To get this numerator, what I do is, I apply x square equal to 1 everywhere except in this. X square equal to minus 4 everywhere except in this. Am I right? You have a formula for integrating 1 by x square minus 1. You have another for integrating 1 by x square plus 4. Job is finished easily. This shortcut I could apply because I found only even powers of x everywhere in the expression. Suppose your numerator is 2x cube plus 3x minus 1. I cannot try this idea because I will have odd powers here. I will not be able to replace x square by 1 in this expression or in this expression. If you use x square equal to 1 equivalent to x equal to plus or minus 1, there will be ambiguity. Which value you have to use, plus 1 or minus 1? You will not be able to apply this shortcut now. But if the expression involves just one term in numerator and with it you have one odd power, say x, I can use this technique once again. What I do is, I keep the factor x outside, consider only this portion for the purpose of breaking into partial fractions. I will get this. Once the expression is broken into partial fractions, the process of breaking into partial fractions is finished, I will bring the x inside. Okay. No, not now. Will be taken up later when we take up method of substitution. Anything left out under partial fractions? Okay. We will have to assume three partial fractions. In finding the numerator of the last partial fraction, we will have no ambiguity. We can apply our shortcut apply the value x equal to minus 2 everywhere except in this factor, last numerator is obtained easily. Value will be minus 4 plus 1 minus 3 divided by minus 2 minus 1 minus 3 whole square 9 is how much? Minus 1 by 3. There are now two partial fractions remaining, one with the x minus 1 as denominator, other one x minus 1 whole square as denominator. Both these numerators are not obtainable by inspection method, but one of them can be obtained. We can obtain this numerator. We will obtain this numerator applying x equal to 1 everywhere except in this factor. The numerator of the partial fraction corresponding to the highest power of the factor can be obtained by this inspection method. Numerator is obtained as 1. For this I don't have any shortcut. I have to apply the trial and error method of inspection, some idea. Making use of already determined numerators, it will be easier for you to determine this numerator now. Only after determining this numerator we can complete the procedure. Suppose this numerator is a. When you apply common denominators, you will get in numerator a into x minus 1 into x plus 2 plus 1 into x plus 2 minus 1 by 3 into x minus 1 whole square. Am I right? Agreed, I think. I am assuming this numerator is a and applying common denominator. Numerator will become this. I want this numerator to agree with 2x plus 1. I want in both these x square coefficient to be 0. There is no x square term here. X square coefficient is 0. Here also x square coefficient must be 0. But what is the x square coefficient here? It is a, no x square term, minus 1 by 3. A minus 1 by 3 is 0 means suppose your integrand consists of just one factor sin 4x, it will be easily integrable. Just the factor sin x, easily integrable. But you have both the factors present now. It's a product of two functions. It's the product sin 4x into sin x. What to do? No standard formula will be directly applicable, even with the help of the theorem, not possible. So we depend on decomposition. Making use of a transformation formula, we break the integrand into a sum or difference. To sin A sin B, what is the corresponding relevant?
Cos 3x minus cos 5.
Okay. You have three factors now. We get decomposed it in stages. First we will have one pair of factors taken together, broken into a sum. Then we will bring in the third factor, complete decomposition, then take up integration step by step. Which factor you prefer to keep outside? Any one of the three. Sin x, okay. Other remaining product, cos A cos B, 2 cos A cos B is I bring the sin x inside. First factor cos 5x cos 5x sin x. I have provided the required coefficient to 2 cos 5x sin x, 2 cos A sin B. Am I right? Sin A plus B minus sin of A minus B. Next product, cos x sin x. Again, coefficient 2 has been provided. 2 cos x sin x. No transformation formula needed. Directly a double angle formula. Am I right? For sin 6x, an integral is minus cos 6x by 6. For sin 4x, minus sin 4x by 4. For sin 2x, not sin, cos, minus cos 2x by 2. The second factor is not cos, is cos hyperbolic. Same idea, once again repeated. Do you know how to integrate e power 3x into sin 2x? Yes. E power minus 3x into sin 2x? Yes. Rationalize the denominator. What do you get in denominator?
1.
Is each term immediately integrable? Yes. Same idea once again. Rationalize the denominator. Right? Yes. Is each of the terms in numerator immediately integrable? Yes. 3 minus 2x whole to the power half. A function of the form x to the power n with x replaced by linear. Again a function of the same form with x replaced by another linear. I have an advantage. Whenever I take up a particular method, Under that method, I will be dealing with only those problems which are solvable by that method. So whatever function I take up now will be integrable by decomposition method. Next, I will be taking up method of integration by substitution. I will be taking only those functions which can be integrated by substitution method. This advantage you will not have in your examinations. You will have learnt all the methods by that time. So the problem will be that you have to decide whether I have to apply decomposition method or apply integration by parts or or substitution method or reduction formula, then apply that method, then obtain your answer as quickly as possible. I have to depend on decomposition, but how to decompose? One idea that I would suggest is, because you have a single term in denominator, this idea works. You just apply a substitution, not for the purpose of integration, only for the purpose of decomposition. Apply substitution, x plus 1 equal to y square. This is not required for integration. I will not be using it for integration, only for decomposition purpose. Okay, my function to be decomposed is 3 into, I am using x plus 1 equal to y square, so root x plus 1 is y. My numerator is 2x minus 1 whole square, but I am using x plus 1 equal to y square, so x will be y square minus 1, 2x will be 2y square minus 2, minus 1 is 2y square minus 3, whole square is division immediate now? Yes. What is the quotient you are getting? Y cube. What is y cube? Go back to x. Minus 12 by 3, 4. Y. Y is what? X plus 1 to the power half. Plus 9 by 3, 3. 1 by y. What is 1 by y? X plus 1 to the power minus half. Each term required to be integrated is in a standard form, is in the form x to the power n with x replaced by a linear function. Answer is immediate. I already handled this situation earlier. Now, with the help of one additional theorem, a little bit of shortening of our work. Make the x square coefficient 1. Now go for the method of completing squares. Then carry out integration. The advantage now is you have reduced this linear expression into a linear expression with coefficient 1. So the chance of getting lost with that coefficient 1 by a will not be there now. you will be safer. And as it is, if you apply method of completing squares, you will come across a irrational coefficient, root 3x plus something whole square. May be bit inconvenient to deal with such coefficients. Easier now. That's all. Use of a trigonometric identity. Strictly speaking, root 1 minus cos 3x is not root 2 into sin 3x by 2. Instead, it is actually mod of sin 3x by 2. But that detail you may omit now. Simply take it as sin 3x by 2, obtain the integral. If none of the options agree with that, change the sign, make it minus sin 3x by 2, find out. Someone will be the answer. Yes.
Root 2 by 3
Now you don't have a similar half angle formula for the function inside.
cos 2x plus sin 2x.
Okay, one idea may be write that sin 4x as cos of pi by 2 minus 4x. Then you will be able to apply this idea. 1 minus cos theta equal to 2 sin square theta by 2. Remove the radical sign, carry out integration. Or
Cos square 2x plus sin square.
this may be written as sin square 2x plus cos square 2x plus 2 sin 2x cos 2x, and therefore the square root will be simply again modulus. Oh, sorry, I am in a hurry. Yes. Yes, yes. Write it as secant square minus 1. Good. Make use of the identity for sin 3x. Sin 3x is 3 sin x minus 4 sin cube x. So sin cube x will be 1 by 4 of 3 sin x minus sin 3x. Use it, you will be able to find it as a linear expression, carry out integration. Multiply numerator and denominator by 1 minus cos 3x. You will get it as 1 minus cos 3x by sin square 3x, which can be decomposed as 1 by sin square 3x minus cos 3x by sin square 3x, which is cosecant square 3x minus cot 3x into cosecant 3x, each term immediately integrable. Or write 1 plus cos 3x as 2 cos square 3x by 2. It will be integrand will be half of secant square 3x by 2. integration immediate. You will get the answer in terms of 3x by 2, in terms of a trigonometric function of 3x by 2. In the other case, you will get the answer in terms of trigonometric functions of 3x. Depending on your requirement, you choose your method. An infinite sum I am having. Is the function that I am asked to integrate, is it in any particular form, standard form? Yes, it is a geometric progression. It is a geometric progression with first term 1 common ratio sin 3x. Is the common ratio in numerical value less than 1? Sin 3x, is it a number less than 1? Yes. Therefore, is the series summable? Yes. The sum to infinity will be 1 by 1 minus sin 3x. One idea may be, write the numerator as sin square 3x by 2 plus cos square 3x by 2 plus 2 sin 3x by 2 cos 3x by 2, which is the square of, okay, no need to square, keep it as it is. Denominator is 2 cos square 3x by 2. Divide each term now by 2 cos square 3x by 2. Sin square 3x by 2 by cos square 3x by 2 is tan square 3x by 2, may be written as secant square minus 1 integrated. Then next term cos square 3x by 2 by cos square 3x by 2 is a pure constant, immediately integrable. Last term 2 sin 3x by 2 by cos 3x by 2, 2 sin 3x by 2 into cos 3x by 2 divided by 2 cos square 3x by 2 is tan into secant, I think. Am I right? Is it simply tan? Oh yes, it is simply tan. Again, a ready-made formula is there. Integral tan is well known to us, is available in the list of standard results. We can integrate. One correction, no need to write this 1 as sin square plus cos square. We can retain it. This is 2 cos square 3x by 2. 1 by 2 cos square 3x by 2 is direct secant square 3x by 2, directly integrable. No need to break this. Only this you need write as 2 sin 3x by 2 cos 3x by 2. Or if you are uncomfortable with secant, very simple now. Write sin 4x as 2 sin 2x cos 2x. Further, sin 2x as 2 sin x cos x. The cos x of denominator will get cancelled. You will be left with the product of 3 trigonometric functions in numerator. Go on applying transformation formula, break it into a sum, carry out the integration. Yes. Are you getting just this much? Yes. Only 2 terms. Okay. Decomposition, only one decomposition gives you the required form. or my function is sin 3x by sin 2x into sin 5x. Directly not integrable. Integrand is not in a standard form. I have to decompose it.
Minus 2 by cos equaling square denoted as sum and partial fractions.
Partial fractions is not a rational algebraic fraction. I think you are only using wrong terms, but you are giving the right idea. You just leave the denominator as it is. Write the numerator sin 3x as sin of 5x minus 2x. Use the expansion formula sin of a minus b equal to sin a cos b minus cos a sin b. Perform term by term division. Sin 5x cancels, leaving cot 2x, directly integrable. In this case, sin 2x cancels, you are left with cot 5x, again directly integrable. Multiply
Divided by sin of
leave the denominator. Consider the arguments in the denominator. Do you notice that their difference is a number, pure number, a constant? How much is the difference? 1. I will multiply numerator and denominator by sin of 1. Sin of 1 is a constant, so I can write it even outside the integral sign. That will not change the or affect the value of the integral. Inside, I will write it in the numerator of the integrand as sin of on expansion what is this divided by this? Sin 2x minus 3, sin 2x minus 3 cancel, leaving cot 2x minus 4, directly integrable. In this case, sin 2x minus 4 gets cancelled, leaving cot 2x minus 3, again a integrable, directly integrable function. Had you used, instead of this sin function, suppose you used cos function, what will happen? Expansion will become cos a cos b minus sin a sin b. The first quotient will be cot a cot b, of the form cot a cot b, not immediately integrable. The method will fail. The function to be used as a multiplier must be chosen properly. Arbitrary choice will not help you in the process. Actually, I wanted to first use cos, show the failure, then change it to sign. It didn't work. Same idea once again. Yes? Any hint? Any suggestions?
Sin of 3 minus x plus 3.
Write the numerator as
Minus of sin of 3 minus.
you can avoid the minus sign, that occurrence of minus sign. Is not cos of minus theta same as cos theta? You change the sign of the argument of the trigonometric function in denominator. You have it as cos of x minus 3. There will be no need to bring in a negative sign. Okay, what next? You will write the numerator sin x as sin of x minus 3 plus 3 and expand it. Okay. I think I have covered all possible combinations which come under the decomposition method by this. Enough. More examples will be taken up when you will be provided with problem sheets. There you will find a greater variety of problems that can be solved with the decomposition method. For the present, as far as discussion of the method is concerned, this much is enough.